Tonight, we are going to look at the place you have lived your entire life without ever truly seeing it. Not your city, not your country, not even your planet. We are going to look at the galaxy, the Milky Way, the vast, ancient, spinning structure of gas and dust and hundreds of billions of suns that contains everything you have ever known, everyone who has ever lived, and every world we have ever pointed a telescope toward. You have probably seen images of it, the long, pale smear stretched across a dark summer sky, faint and ghostly, easy to overlook if you live anywhere near artificial light. And if someone asked you how big it is, you might say something like, well, it is 100,000 light years across, which is the number that appears in textbooks and encyclopedias and science documentaries. 100,000 light years. It sounds immense. It sounds final. It sounds like the kind of number that settles a question rather than opens one. But here is what nobody tells you. That number is wrong. Not slightly wrong, not off by a few percent. Wrong in a way that changes the entire character of the galaxy you live inside. Over the past 2 decades, and especially in the past several years, a series of discoveries has forced astronomers to fundamentally revise their understanding of the Milky Way's true extent. The real galaxy, the full structure from its ancient heart to its outermost reaches, is not 100,000 light years across. It is not even close. The number that has emerged from the most precise measurements ever made of our galaxy's boundaries stretches toward 2 million light years, and some of the evidence points further still. By the time this is over, you will understand why that old number was so confidently wrong for so long. You will understand what lies beyond the bright disk of stars that most people think of as the whole galaxy. You will understand the invisible structures, the ancient streams of stars, the buried halo of matter so diffuse it was nearly impossible to see, that extend outward into the darkness for distances that dwarf everything we thought we knew. And you will understand why getting this right matters, not just as an act of cosmic cartography, but as a window into the history of the universe itself, into how galaxies form, how they grow, and what eventually becomes of them. Let us start with what we thought we knew and why we thought it so confidently for so long. If you want to understand how astronomers measured the Milky Way for most of the 20th century, you have to understand the problem they were working against. We are inside the galaxy. That single fact makes measuring it extraordinarily difficult in a way that has no real parallel in everyday experience. Imagine trying to map the shape of a forest you are standing in the middle of, surrounded on all sides by trees, unable to climb above the canopy, unable to see its edges directly. You can see the trees nearest to you clearly. You can see the ones a bit further away. But eventually the density of the forest itself blocks your view, and everything beyond a certain distance becomes invisible. The Milky Way is a disk of gas and dust and stars, and that dust is the cartographer's nemesis. Ordinary visible light cannot pass through it freely. The dust absorbs and scatters light, dimming distant stars, and sometimes hiding them entirely. For much of the 20th century, astronomers working with optical telescopes could not see through the plane of the galaxy at all. Entire regions of our own home galaxy were simply invisible to them. The center of the Milky Way, for example, is hidden behind so many layers of obscuring dust that it is essentially opaque to visible light. You could stare directly toward the galactic center on the clearest night of your life and see nothing of what lies there. Given these constraints, the measurements that emerged across the middle decades of the 20th century were genuinely impressive achievements. Astronomers developed indirect methods using the distribution of star clusters, the rotation of gas clouds, the pattern of radio emissions, to build a map of the galaxy they could not directly see. And the picture that emerged was broadly correct in its major features. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend outward like the arms of a pinwheel. Our solar system sits roughly 26,000 light-years from the galactic center, well out in one of the spiral arms in a relatively quiet neighborhood, far from the densest regions of stellar activity. The diameter that became canonical, approximately 100,000 light-years, was derived from tracing the extent of this bright disk, the region where stars and gas and dust are densely enough concentrated to be clearly organized into the spiral structure. It was a reasonable measurement of a real thing. The trouble was that it was measuring the wrong thing. It was measuring the most visible part of the galaxy, the luminous disk, and treating that as if it were the whole galaxy. What lay beyond the disk was not nothing. It was something far harder to see, far harder to measure, and far vaster than anyone had initially suspected. The concept that would eventually force a rethinking of the galaxy's true size had been developing in the background of astrophysics for decades before it became undeniable. It goes by the name dark matter, and if you have heard the term before, you may have heard it described primarily in terms of its gravitational influence on galaxy rotation, which is how it was first conclusively inferred. But dark matter is not just an explanatory patch applied to the rotation curves of galaxies. It is a physical structure, a vast invisible halo that envelops every galaxy we know of, extending far beyond the luminous stellar disk and containing a mass that dwarfs the combined mass of all the stars, gas, and dust it surrounds. The evidence for this halo came initially from a surprising observation about how galaxies rotate. When astronomers in the 1960s and 1970s began measuring the orbital velocities of gas and stars at different distances from the centers of spiral galaxies, they expected to find a particular pattern. The logic was straightforward. If the mass of a galaxy is concentrated in its visible stars, which are themselves concentrated toward the center, then stars further from the center should orbit more slowly than stars closer in. Just as the outer planets of our solar system orbit the Sun more slowly than the inner planets do, this is what Newtonian gravity and Kepler's laws predict, and it works perfectly when mass is centrally concentrated. What the measurements showed was something entirely different. Astronomer Vera Rubin, working with her colleague Kent Ford, measured the rotation curve of the Andromeda Galaxy and found that stars far from the center were moving just as fast as stars much closer in. Not slightly faster than expected, just as fast. The velocity curve, instead of falling off with distance as it should have, stayed flat. And as more galaxies were measured, the same flat rotation curve appeared again and again. This was not a measurement error, it was a systematic feature of how galaxies actually behave. And the only explanation that made physical sense was that each galaxy is embedded within a halo of invisible mass, distributed far beyond the visible disk, providing additional gravitational pull that keeps the outer stars moving at the velocities they actually have. Without this invisible mass, the outer regions of galaxies would fly apart. With it, they hold together, rotating as they do. For the Milky Way specifically, estimating the size and mass of this dark matter halo was a project that occupied astronomers for decades, and it produced a wide range of answers depending on the methods used. But the consistent finding was that the dark matter halo extends far beyond the luminous disk, not by a little, by an enormous margin. Where the stellar disk ends at roughly 50,000 light-years from the center, the dark matter halo continues outward, past 100,000 light-years, past 200,000, and by some estimates past 500,000 light-years from the galactic center. If the luminous disk is the visible tip of the iceberg, the dark matter halo is the enormous submerged mass beneath it, invisible but real, and gravitationally dominant. But dark matter alone could not give astronomers a direct measurement of the galaxy's true outer boundary, because it cannot be seen directly. What changed the measurement problem fundamentally was the discovery that the halo is not purely dark. It contains stars, ancient, sparse, difficult to detect, spread across extraordinary volumes of space, but real stars, real luminous objects that could in principle be found and mapped if the technology to find them could be developed. And in the first 2 decades of the 21st century, that technology arrived. The instrument that changed everything was not a single telescope, but a survey. The Sloan Digital Sky Survey began operations in the year 2000 and used a dedicated telescope in New Mexico to systematically image a quarter of the entire sky in 5 different wavelengths of light. It was not the largest telescope ever built, and it was not the most sensitive. What made it revolutionary was its systematic completeness and the sheer volume of data it produced. Where previous sky surveys had mapped tens of thousands of objects, the Sloan survey catalogued hundreds of millions, eventually more than 1 billion individual sources, building a 3-dimensional map of the observable universe that dwarfed anything that had come before it. Within this ocean of data, astronomers began finding things they had not expected. Faint structures in the outer regions of the Milky Way, streams of stars that seemed to follow curved paths through the halo, looping around the galaxy in great arcs that did not correspond to any known feature of the bright disk. Overdensities, regions where the density of certain types of stars was higher than the smooth background would predict, hinting at structures that had been mixed into the halo but not yet fully dispersed. The halo was not smooth. It was not empty. It was, in fact, filled with the traces of ancient events, the gravitational record of things that had happened to the Milky Way over the course of its entire lifetime. The most significant of these ancient traces, and the one that would eventually play a central role in revising the galaxy's true size, was the discovery of what astronomers call stellar streams. To understand what a stellar stream is, you need to understand what happens when a small galaxy or a dense cluster of stars wanders too close to a much larger one. Gravity is not a gentle force at galactic scales. When a small satellite galaxy or a globular cluster, which is a tightly bound sphere of hundreds of thousands of ancient stars, falls into the gravitational field of a large galaxy, like the Milky Way, the larger galaxy does not simply capture it whole. Instead, it pulls at it differentially. The near side of the incoming object feels a stronger gravitational pull than the far side. This difference in pull, what physicists call a tidal force, stretches the smaller structure out along its orbital path. Stars are drawn forward along the orbit and backward along the orbit, peeled away from the cluster or dwarf galaxy over millions of years, leaving a thin ribbon of stars tracing the path the original object took as it spiraled inward. That ribbon is a stellar stream. They are extraordinarily difficult to detect. The stars within them are spread across volumes of space so large that their surface density on the sky can be just a few stars per square degree. barely distinguishable from the background population of halo stars without careful statistical analysis. For most of the 20th century, the technology to find them simply did not exist. The Sloan survey changed that by providing a uniform, deep, well-calibrated map of hundreds of millions of stars across a quarter of the sky. It gave astronomers the statistical foundation they needed to find these faint overdensities against the background. The first major discovery came in the year 2002, when a team of astronomers analyzing Sloan data found an enormous ring of stars encircling the Milky Way in the plane of the galactic disk. They called it the Monoceros Ring, named for the constellation in whose direction a significant portion of it lay. It was unlike anything in the established picture of the galaxy. It was too far from the center to be part of the disk, too regular to be a chance overdensity, and too massive to be a typical globular cluster stream. It appeared to encircle the entire galaxy, a ring of stars at a distance of roughly 60,000 light-years from the galactic center, sitting just outside the edge of what had been considered the main disk. The debate about what the Monoceros Ring actually is has continued for years. Some astronomers argued it was the remnant of a disrupted dwarf galaxy, a satellite galaxy that had been torn apart by tidal forces as it spiraled through the outer disk. Others argued it was a warped and flared extension of the disk itself, a natural consequence of the disk's outer edges being disturbed by interactions with satellite galaxies. Still others proposed it was a combination of both. What everyone agreed on was that it was real, it was enormous, and its existence meant that the boundary between the disk and the halo was far less sharp and far further out than the canonical picture had assumed. But the Monoceros Ring was only the beginning. As the Sloan survey data accumulated and as new surveys extended its coverage, more structures appeared. Stellar streams were found in the halo at distances of tens of thousands of light-years from the galactic center. Overdensities of old metal-poor stars, the kind that formed in the earliest epochs of the galaxy's history, were mapped across vast volumes of the outer halo. One of the most dramatic finds was the Sagittarius stream, the debris trail left by the ongoing tidal disruption of the Sagittarius dwarf galaxy, a small satellite galaxy that is currently being consumed by the Milky Way. The stream from this disruption wraps around the entire galaxy in great loops, extending to distances of more than 100,000 light-years from the center, tracing an orbit that has taken the Sagittarius dwarf through multiple passages close to the galactic disk over billions of years. Each passage stripped more stars from the dwarf galaxy and added them to the stream. The result is a structure of extraordinary length, a river of stars hundreds of thousands of light-years long, curving around the Milky Way in a great arc that passes through both the northern and southern hemispheres of the halo. Finding it required piecing together data from multiple surveys and multiple sky regions, but once it was assembled, it became one of the most powerful tools available for measuring the mass and extent of the Milky Way, because the shape of a tidal stream is exquisitely sensitive to the gravitational field it is orbiting within. Now, to appreciate what these discoveries were really measuring, you need to understand what astronomers mean when they talk about the boundary of a galaxy. This is not a trivial question. A galaxy does not have a surface. There is no wall, no edge, no place where the last star ends and empty space definitively begins. Instead, a galaxy's extent is defined by a theoretical boundary called the virial radius, sometimes also called the splashback radius in more recent usage, which represents the distance from the galactic center at which the gravitational influence of the galaxy becomes comparable to the general gravitational environment of the surrounding large-scale structure of the universe. Inside this radius, material is gravitationally bound to the galaxy. It orbits the galaxy, falls toward it, or has been incorporated into it. Outside this radius, material is either escaping the galaxy's gravitational influence entirely or is more strongly influenced by neighboring structures. The virial radius is therefore the most physically meaningful definition of a galaxy's true size. The radius within which the galaxy's gravity dominates, and it encompasses not just the luminous disk and the stellar halo, but the full extent of the dark matter halo as well. For the Milky Way, estimating this radius requires knowing the total mass enclosed within different distances from the galactic center, which in turn requires using tracers, objects whose velocities and positions can be measured and whose behavior under gravity can be used to infer the gravitational potential they are moving within. Stellar streams are among the best tracers available, precisely because their morphology, their shape, their width, their length, how quickly they disperse, is all a direct record of the gravitational field they have moved through. A stream that remains narrow and coherent over hundreds of thousands of light-years of orbit tells you something specific about the distribution of mass it has been orbiting within. A stream that fans out quickly tells you something different. Using streams, globular clusters, and the velocities of the most distant stars detectable in the halo, astronomers over the past 2 decades have assembled progressively more precise estimates of the Milky Way's total mass and true radius, and the answers that have emerged are consistently larger than the earlier estimates suggested. A landmark study published in 2019 using data from the European Space Agency's Gaia satellite, combined with the velocities of globular clusters and satellite galaxies measured by the Hubble Space Telescope, placed the total mass of the Milky Way at approximately 1.5 trillion solar masses, with the dark matter halo extending to a virial radius of somewhere between 600,000 and 1 million light-years from the galactic center. 1 million light-years. Hold that number for a moment. The old textbook number for the galaxy's diameter was 100,000 light-years. The virial radius alone, just the radius, not even the full diameter, is now estimated at somewhere between 600,000 and 1 million light-years. The full diameter of the gravitationally bound structure we call the Milky Way is therefore somewhere between 1.2 million and 2 million light-years, depending on the measurement method and the definition of boundary used. That is a galaxy between 12 and 20 times larger than the version that appeared in textbooks for most of the 20th century. Not 20% larger, not twice as large, potentially 20 times as large. The structure you are living inside is so vast that even the language we use to describe large numbers begins to feel inadequate. But there is a further layer to this. The dark matter halo is not the only extended structure associated with the galaxy. Surrounding even the dark matter halo and extending further still is a region of extremely hot, diffuse gas called the circumgalactic medium. This is not a vacuum. It is a plasma, a sparse but real physical structure composed primarily of hydrogen and helium at temperatures of hundreds of thousands to millions of degrees Kelvin, and it extends in all directions from the galaxy's center to distances that may reach 1 million light-years or beyond. The circumgalactic medium is part of the galaxy's ecosystem, fed by gas flowing out from supernova explosions and the activity around the central black hole, and feeding the galaxy in return by providing a reservoir of gas that can eventually cool, condense, and fall back into the disk to form new stars. Detecting it required instruments sensitive to X-ray wavelengths, because gas at millions of degrees Kelvin does not emit visible light. It glows in X-rays, and the maps that have been built using X-ray observatories have confirmed that this hot gas corona surrounding the Milky Way is not a thin wisp. It contains a mass of gas estimated to be comparable to the mass of all the visible stars in the galaxy, several 100 billion solar masses, distributed across a sphere that dwarfs the stellar disk by a factor of 10 to 20 in radius. When you combine the luminous disk, the stellar halo with its streams and ancient populations, the dark matter halo, and the circumgalactic medium, the picture that emerges is one of extraordinary nested complexity, structure within structure within structure, each layer extending further from the center than the last, each one containing its own physical processes and its own record of the galaxy's history. The galaxy is not a flat disk of stars surrounded by emptiness. It is an onion of cosmic proportions, its outermost layers so vast and so diffuse that detecting them at all represents one of the great technical achievements of modern astronomy. To understand why the Milky Way grew so large over its lifetime, you have to go back to the beginning. Not the beginning of the galaxy as we know it today, with its elegant spiral arms and its orderly disk of stars, but the beginning of everything. The earliest moments after the Big Bang, when the universe was a nearly uniform sea of hydrogen and helium threaded through with tiny fluctuations in density that would eventually become everything we see around us. The universe is approximately 13.8 billion years old. In the first few 100 million years after the Big Bang, there were no galaxies, there were no stars, there was only gas. The primordial hydrogen and helium produced in the first few minutes of the universe's existence, slowly cooling as the universe expanded, beginning to respond to the tiny density fluctuations that had been imprinted on it during the inflationary epoch that preceded the Big Bang itself. Where the density was slightly higher than average, gravity was slightly stronger than average. Gas began to flow toward these overdense regions. Over millions of years, these flows converged, creating filaments and sheets of gas, with great voids emptying out between them. This large-scale structure, the cosmic web as it is called, is the scaffolding on which all galaxies formed. At the intersections of the filaments, where flows of gas converged from multiple directions, the density became high enough for gas to cool rapidly, contract, and fragment into the first stars. These first stars were nothing like the Sun. They formed from gas that contained only hydrogen and helium, with none of the heavier elements that make up planets and organic chemistry, and they were extraordinarily massive by the standards of stars today, some of them hundreds of times the mass of the Sun. They burned through their nuclear fuel in just a few million years, ending their lives in catastrophic explosions that seeded the surrounding gas with the first heavy elements ever forged in a stellar interior. The first galaxies that assembled around these early episodes of star formation were tiny by present standards. They contained perhaps a few million to a few 100 million solar masses of stars and gas, spread across regions just a few thousand light-years across. They were not the grand spirals we see in images of nearby galaxies today. They were irregular, turbulent, constantly merging with each other as the dense regions of the cosmic web continued to attract more mass, and the structures within them grew through repeated collisions and accretion. The Milky Way we live in today is the product of billions of years of this process. It did not form all at once. It assembled hierarchically, small structures merging to form larger ones merging to form still larger ones, each merger adding mass and stars and gas and dark matter to the growing whole. The stellar halo that now extends hundreds of thousands of light years from the galactic center is in large part a museum of this process, a record written in the positions and velocities and chemical compositions of ancient stars that were once part of smaller galaxies, now dispersed and mixed into the halo of the much larger structure that consumed them. The oldest stars in the Milky Way are more than 13 billion years old, formed in the earliest episodes of star formation when the universe was less than 1 billion years old. Some of these stars exist in the central bulge of the galaxy, densely packed in a region just a few thousand light-years across. Others are scattered through the halo in globular clusters, spherical swarms of hundreds of thousands of stars that represent the dense cores of the first galaxies to fall into and merge with the proto-Milky Way. These globular clusters are extraordinary objects. The Milky Way contains approximately 150 known globular clusters, each one a fossil fragment of the galaxy's earliest history, preserved in the outer halo, where the tidal forces of the disk are too weak to tear them apart. When astronomers measure the chemical compositions of stars in these clusters, they find exactly what the hierarchical assembly picture predicts. The oldest clusters contain stars made almost entirely of hydrogen and helium, with only trace amounts of heavier elements. The younger clusters contain stars progressively enriched with heavier elements, the accumulated output of generations of stars that lived and died before them. This chemical gradient through time, written in the spectra of stars scattered across the halo, is one of the most powerful lines of evidence for the history of the galaxy's assembly, a record of the progressive enrichment of the galaxy's gas supply over billions of years of stellar evolution. But the halo is not composed only of globular clusters and their dissolved remnants. Much of the stellar mass in the outer halo consists of stars that were once part of dwarf galaxies, small satellite galaxies that fell into the Milky Way's gravitational field over the course of its history and were torn apart by tidal forces. The stellar streams discovered by the Sloan survey and subsequent instruments are the most visible evidence of this ongoing process, but the bulk of the halo's stellar population is thought to have come from mergers that happened so long ago that the streams from them have completely phase-mixed. Their stars spread so uniformly through the halo that the original structures are no longer recognizable as streams. Reconstructing this merger history is one of the most active areas of research in galactic astronomy today, and it took a dramatic step forward with the release of data from the Gaia satellite. Gaia was launched by the European Space Agency in December of 2013 and began its primary science mission in 2016. Its purpose was to measure the positions, parallaxes, and proper motions of more than 1 billion stars in the Milky Way with an accuracy that far exceeded anything previously achievable. To give you a sense of what that precision means, Gaia was capable of measuring the angular position of a star with an uncertainty equivalent to the angles subtended by a human hair seen from a distance of 1,000 kilometers. The data from Gaia's first and second major releases, published in 2016 and 2018 respectively, transformed our understanding of the Milky Way's structure and history almost overnight. Among the most stunning discoveries hidden in the Gaia data was evidence for a massive ancient merger event that astronomers named Gaia Enceladus, or sometimes the Gaia sausage, because of the distinctive elongated shape its stars trace out in a particular diagram of orbital energy versus angular momentum. The evidence showed that sometime between 8 and 11 billion years ago, the young Milky Way underwent a head-on collision with a galaxy that was itself not small. Estimates of the mass of the Gaia Enceladus galaxy at the time of merger suggest it contained somewhere between 500 million and 1 billion solar masses of stars, making it comparable in mass to the Large Magellanic Cloud, the largest of the Milky Way's current satellite galaxies. The collision was not a glancing blow. It was a direct impact, and it had profound consequences for the Milky Way's structure. The stars from Gaia Enceladus now constitute a significant fraction of the Milky Way's inner stellar halo, the region of the halo within about 30,000 light-years of the galactic center. They have distinctive kinematics, meaning their orbital properties are different from the stars that formed in situ within the proto-Milky Way, and their chemical compositions mark them as having formed in a galaxy with a different chemical enrichment history. The collision also appears to have triggered a major episode of star formation in the Milky Way itself, as the shock of the merger compressed gas in the proto-disk, causing it to collapse and form new stars at an accelerated rate. The thick disk of the Milky Way, a population of older, more chemically enriched stars, distributed in a layer roughly 3,000 light-years thick around the thin disk where the Sun resides, may be in part a product of this merger-induced starburst. Finding this event, something that happened 9 billion years ago and left its traces scattered across a volume of space tens of thousands of light-years across, required precisely measuring the velocities of millions of individual stars and recognizing the statistical patterns hidden within those velocities. It is the kind of forensic reconstruction that would have been impossible even 20 years ago. The fact that it is now possible and that the evidence is clear enough to be unambiguous represents one of the most remarkable achievements in the history of astronomy. And Gaia Enceladus was not the only ancient merger event the data revealed. Subsequent analysis identified additional merger signatures in the Gaia data, each with its own name now, each representing a separate galaxy that fell into the Milky Way at some point in its history. Sequoia, Tamnos, Kraken, each one a ghost galaxy, consumed long ago, its stars now orbiting within the Milky Way's halo, unrecognizable as individuals but detectable as a statistical population with shared orbital and chemical properties. The Milky Way we live in is not a pristine, self-assembled structure. It is a composite, a palimpsest, written over and over again with the material of dozens of smaller galaxies that no longer exist as independent objects. This history of assembly through mergers is not unique to the Milky Way. It is how all large galaxies grow. The hierarchical structure formation that began with tiny density fluctuations in the early universe plays out the same way everywhere, small structures merging to form larger ones over cosmic time. But for the Milky Way, we have the advantage of being inside it, able to study individual stars rather than just the integrated light of a distant system. This proximity makes the Milky Way the most detailed laboratory we have for understanding how galaxies in general work, and the discoveries of the past decade have shown just how rich that laboratory actually is. The outer regions of the halo, beyond 50,000 light-years from the galactic center, tell a different story from the inner halo. Where the inner halo appears dominated by the debris of the Gaia-Enceladus merger and the other ancient accretion events identified in the Gaia data, the outer halo is more heterogeneous, containing a mix of structures at different stages of disruption. Some of the stellar streams in the outer halo are ancient and phase-mixed almost beyond recognition. Others are strikingly fresh, coherent ribbons of stars that can be traced across tens of thousands of light-years of sky, representing ongoing or geologically recent disruption events. The Sagittarius stream, which we encountered earlier, is the most prominent of these fresh structures. The Sagittarius dwarf galaxy itself still exists as a recognizable object, a dense concentration of stars sitting on the far side of the galactic center from our solar system, about 70,000 light-years from us. But it is in an advanced state of disruption. Each time it passes through or close to the galactic disk, the tidal forces strip more stars from it and add them to the stream. The stream now contains more stellar mass than the remnant core of the galaxy itself. Estimates suggest the Sagittarius dwarf has lost somewhere between 80 and 90% of its original stellar mass to the stream over the course of its multiple orbital passages. The stream loops around the entire galaxy in a great circle, with two distinct wraps visible in current data, one in the northern galactic hemisphere and one in the southern, the older wrap having faded and dispersed further than the more recent one. Stars from the Sagittarius stream have been found at distances of more than 150,000 light-years from the galactic center in some directions, tracing the outermost portions of the Sagittarius dwarf's most recent orbital excursion before it fell back toward the center. These are among the most distant individually identified stars known to belong to the Milky Way's gravitationally bound system. The question of where exactly the Milky Way ends, the precise location of that outer boundary we discussed earlier, is not merely a matter of drawing a line on a map. It is a question that requires understanding the gravitational relationship between the Milky Way and its neighbors, because a galaxy's boundary is defined not by where its last star sits, but by where its gravitational dominance gives way to the gravitational dominance of everything else around it. And for the Milky Way, that relationship with its neighbors is more complex, more dynamic, and more consequential than most people realize. The Milky Way is not alone. It is the dominant member of a collection of galaxies called the Local Group, a gravitationally bound assembly of more than 50 galaxies spread across a volume of space roughly 10 million light-years in diameter. Most of the galaxies in the Local Group are small, dwarf galaxies containing anywhere from a few million to a few billion stars, orbiting in the gravitational fields of the two dominant members. Those two dominant members are the Milky Way and the Andromeda Galaxy, also known by its catalogue designation Messier 31. Andromeda is the Milky Way's sibling in the most meaningful sense. It is a spiral galaxy of comparable size and mass, sitting approximately 2.5 million light-years away from us in the direction of the constellation Andromeda. On clear, dark nights, it is visible to the naked eye as a faint smudge of light, the most distant object a human being can see without optical aid. That faint smudge contains roughly 1 trillion stars, somewhat more than the Milky Way, and like the Milky Way, it is surrounded by a vast, dark matter halo, a stellar halo filled with streams and ancient populations, and a hot gas corona extending hundreds of thousands of light-years in all directions. The distance between these two giants, 2.5 million light-years, sounds like an enormous buffer. But when you consider that each of their dark matter halos extends somewhere between 600,000 and 1,000,000 light-years from its respective center, you begin to see that the gap between them is not as vast as it first appears. The outermost regions of the Milky Way's dark matter halo and the outermost regions of Andromeda's dark matter halo may already be in contact, or very nearly so. The two galaxies are not isolated islands in a void, they are neighbors whose gravitational reach overlaps, and they are moving toward each other. This last point deserves careful attention because it is one of the most consequential facts about the future of our galaxy. The Milky Way and Andromeda are approaching each other at a speed of approximately 110 kilometers per second in the radial direction, meaning directly toward each other, with an additional transverse component that has been measured with increasing precision using Hubble Space Telescope observations of Andromeda's proper motion across the sky. The best current measurements suggest that the two galaxies will begin their first close approach in approximately 4.5 billion years, and that a full merger will be completed somewhere between 6 and 10 billion years from now. This is not a speculative scenario. The gravitational dynamics are well understood, the velocities are measured, and the outcome is determined by physics that has been tested in countless other galaxy systems we can observe at various stages of merger. What we see when we look at colliding and merging galaxies elsewhere in the universe is what awaits the Milky Way and Andromeda. The result, which astronomers have already given a name, Milky, will be a single, large elliptical galaxy. The organized spiral structure of both predecessors thoroughly scrambled by the violence of the interaction, the combined stellar populations redistributed into the smooth, rounded shape characteristic of elliptical galaxies. The Sun will almost certainly survive this event. Stellar collisions during galaxy mergers are extraordinarily rare because the distances between individual stars, even in the densest regions of a galaxy, are so vast that the probability of two stars physically colliding during a merger is vanishingly small. But the orbital position of the Sun within the resulting galaxy will be completely unpredictable. Computer simulations of the merger suggest a range of possible outcomes for any given star, from remaining at roughly its current distance from the combined galactic center to being flung outward into the halo, to being drawn inward toward the central regions where the two supermassive black holes from each galaxy will eventually themselves merge in a cataclysm of gravitational wave radiation. What all of this means for the question of the galaxy's current size is that the Milky Way exists in a dynamic relationship with its surroundings that makes its boundary a living, changing thing, rather than a fixed property. The dark matter halos of the Milky Way and Andromeda are already exerting significant gravitational influence on each other across the space between them. The dwarf galaxies scattered through the local group are responding to the combined gravitational field of both dominant members. Some of these dwarfs are in stable long-term orbits. Others are on trajectories that will eventually bring them close enough to be disrupted. Still, others may be passing through the local group for the first time, falling in from the surrounding intergalactic medium on orbits that will ultimately end in their incorporation into one of the two large galaxies or the merged remnant that will eventually replace them. Sitting in the midst of this dynamic system with its overlapping halos and its ongoing minor mergers and its eventual cataclysmic major merger is our solar system, on a roughly circular orbit around the galactic center at a distance of approximately 26,000 light-years, completing one full orbit approximately every 225 million years. In the 4.5 billion years since the solar system formed, it has completed roughly 20 orbits of the galaxy. In the 4.5 billion years remaining before the Andromeda merger begins, it will complete approximately 20 more. Now, let us turn to the specific observational techniques that have allowed astronomers to push the measurement of the galaxy's outer boundary further and further from the centre, because understanding how we know what we know is inseparable from understanding what we know. The challenge of measuring the outer halo is fundamentally a problem of finding objects that are both detectable across vast distances and useful as tracers of the gravitational potential they are moving within. The most powerful individual tracers currently available are a class of stars called RR Lyrae variables. These are old, low-mass stars that have evolved off the main sequence and are undergoing regular pulsations, rhythmically expanding and contracting in a way that causes their brightness to vary with a period of between about 6 hours and about 1 day. What makes them invaluable for distance measurement is that their intrinsic luminosity, the total amount of light they actually emit, is nearly constant from one RR Lyrae star to another. They are, in the language of astronomy, standard candles, because RR Lyrae stars all have nearly the same intrinsic brightness. Measuring how bright one appears from Earth directly tells you how far away it is. A star that appears 4 times fainter than another RR Lyrae star is twice as far away, following the inverse square law of light propagation. With precise photometry from a modern wide field survey, individual RR Lyrae stars can be identified and their distances measured with uncertainties of just a few %, even at distances of hundreds of thousands of light years. The distribution of RR Lyrae stars in the outer halo has been one of the primary tools used to map the galaxy's stellar extent at large radii. And the picture that has emerged from the most sensitive surveys is one that consistently places stellar material associated with the Milky Way at distances that were considered extraordinary just 2 decades ago. RR Lyrae stars have been found at distances of more than 300,000 light-years from the galactic centre in some directions. Others have been found at distances approaching 400,000 light-years. Whether all of these stars are genuinely bound to the Milky Way, or whether some are associated with the Magellanic Stream, a vast ribbon of gas and stars connecting the Milky Way to the large and small Magellanic Clouds, is a question that requires careful analysis of each star's kinematics as well as its position. The Magellanic Clouds themselves are central to any discussion of the Milky Way's outer structure. The Large Magellanic Cloud sits approximately 160,000 light-years from the galactic centre. The Small Magellanic Cloud sits approximately 200,000 light-years away. Together, they are the Milky Way's 2 largest satellite galaxies, visible to the naked eye from the southern hemisphere as detached patches of the Milky Way's light, distinct but clearly associated with the larger galaxy they orbit. For decades, astronomers assumed the Magellanic Clouds were old companions of the Milky Way, having orbited it for billions of years through multiple passages. This assumption influenced how their structural effects on the Milky Way were interpreted. But measurements from the Hubble Space Telescope, published in the mid-2000s, revealed that the Magellanic Clouds are moving significantly faster than expected for objects on long-term bound orbits around the Milky Way. Their velocities suggested that rather than being ancient companions, they may be relatively recent arrivals, falling into the Milky Way's gravitational influence for the first time or completing only their first or second orbital passage. If this interpretation is correct, it has profound implications for the Milky Way's outer structure. A more massive Milky Way with a dark matter halo extending further and containing more total mass than older estimates suggested could still hold the Magellanic Clouds on bound orbits despite their high velocities. And the more massive estimates that have emerged from recent work are indeed more consistent with the Magellanic Clouds being gravitationally bound to the Milky Way. This is another example of the interconnectedness of these measurements. The mass estimate affects the boundary estimate, which affects the question of what is bound and what is not, which in turn constrains the mass estimate through the dynamics of the objects that are observed. The Magellanic Stream, the ribbon of gas that trails behind and ahead of the Magellanic Clouds along their orbital path, is one of the most prominent large-scale structures in the outer Milky Way system. It extends across more than 180 degrees of the sky as seen from Earth, curving away from the clouds in both directions along their orbit, and it has recently been found to extend to distances of several 100,000 light-years from the galactic center in its leading arm. The stream contains an estimated billion solar masses of neutral hydrogen gas, enough raw material to sustain significant star formation if it were to fall into the disk of the Milky Way intact, which it eventually will as the Magellanic Clouds complete their infall and are disrupted. Understanding the full three-dimensional extent of the Magellanic Stream, its origin in the tidal and ram pressure stripping of the Magellanic Clouds, and its future fate as it mixes into the Milky Way's gas supply, is an active area of research that touches directly on the question of the galaxy's outer boundary. Because the stream is so vast, so massive, and so extended, it effectively adds to the inventory of material that must be considered part of the Milky Way's gravitational domain, even though it has not yet settled into any organized structural component of the galaxy. There is a particular kind of star that sits at the extreme edge of what we can currently detect in the outer halo, and its existence there raises a question that cuts to the heart of what we mean when we say a star belongs to a galaxy. These stars are called hypervelocity stars, and their story begins not at the outer edge of the galaxy, but at its very center, in the immediate vicinity of the supermassive black hole that anchors the entire structure. Sagittarius A star, the supermassive black hole at the center of the Milky Way, contains a mass of approximately 4 million solar masses, compressed into a region smaller than the distance between the Sun and the orbit of Mercury. It is not the largest black hole known. Galaxies more massive than the Milky Way typically harbor central black holes with masses of hundreds of millions to billions of solar masses. But 4 million solar masses concentrated in such a small volume creates a gravitational environment of extraordinary intensity in the immediate vicinity of the galactic center, a place where the physics of gravity operates in regimes that have no parallel anywhere else in the galaxy. One of the consequences of this extreme gravitational environment is a mechanism for producing stars moving at velocities that are completely impossible to achieve through any ordinary dynamical process. The mechanism was first proposed theoretically by astronomer Jack Hills in 1988, more than a decade before the first hypervelocity star was actually found. Hills recognized that binary star systems, pairs of stars orbiting each other, occasionally wander close enough to the central black hole to experience a tidal interaction. In this interaction, the black hole captures one member of the binary while the other is flung outward at an enormous velocity. The gravitational energy of the binary's internal orbit converted by the interaction into the kinetic energy of the ejected star. The velocities involved are staggering. A star ejected through this Hill's mechanism can be launched at speeds of anywhere from 500 to more than 1,000 kilometers per second. The escape velocity from the Milky Way at the distance of the Sun from the galactic center is approximately 550 kilometers per second. A star moving at 700 or 800 kilometers per second from the galactic center will escape the galaxy's gravitational well entirely, traveling outward through the halo and eventually into intergalactic space, never to return. The first hypervelocity star was discovered in 2005 by astronomer Warren Brown and his colleagues, who found a star in the outer halo moving at approximately 700 kilometers per second relative to the galactic center, far faster than any star could be moving if it were on a bound orbit. The star was at a distance of approximately 110,000 light-years from the galactic center, already well outside the traditional boundary of the luminous disk and moving outward. Since that initial discovery, more than 24 confirmed hypervelocity stars have been identified, along with hundreds of candidates awaiting confirmation. These objects are important for multiple reasons. First, they are direct observational evidence of the extreme conditions near the galactic center. The rate at which hypervelocity stars are being produced, inferred from the number found and the volume of space that has been searched, is consistent with the Hill's mechanism operating on binary stars that wander into the vicinity of Sagittarius A star at a rate of roughly 1 per 100,000 years. Second, and more relevant to the question of the galaxy's extent, they demonstrate that the outer halo, at distances of 100 to 300,000 light-years from the center, is not a static reservoir of ancient accreted stars. It is a dynamic space being actively populated by stars launched from the galactic center on one-way journeys outward. Third, and most subtly, the trajectories of hypervelocity stars can, in principle, be used as probes of the gravitational potential of the galaxy at large radii. A star that was launched from the galactic center at a known time, which in some cases can be inferred from its stellar age and the properties of the population it came from, has traveled through the galaxy's gravitational field for that entire time. The velocity it has now reflects the cumulative effect of the galaxy's gravity on its outward journey. By modeling the expected trajectory given different assumptions about the dark matter halo's mass distribution and comparing to the observed velocity, astronomers can constrain the halo's properties in the outer regions where other traces are sparse. The existence of hypervelocity stars also highlights a broader truth about the outer halo that is easy to miss when thinking about the galaxy purely in terms of its average properties. The outer halo is not a well-mixed equilibrium structure. It is a superposition of populations with wildly different origins, velocities, and future fates. Some of its stars are ancient, accreted from dwarf galaxies billions of years ago and now unstable, long-period orbits that will keep them associated with the Milky Way essentially forever on any timescale relevant to human civilization, or even to the remaining main sequence lifetime of the Sun. Others are relatively recent additions torn from dwarf galaxies that are being disrupted right now, still moving in coherent streams that will eventually phase mix into the background halo over the next few billion years. And others still are transients, hypervelocity stars that are gravitationally unbound and simply passing through the outer halo on their way out into intergalactic space, here for a cosmic moment before they disappear into the void between galaxies. This heterogeneity is one of the reasons that measuring the outer boundary of the Milky Way is so conceptually subtle. The virial radius, the gravitational boundary we discussed earlier, is a physically well-defined quantity. But the stellar population within it at any given moment is a mixture of permanently bound residents and transient visitors. The distinction between them requiring individual velocity measurements rather than just positional data. It is the difference between mapping a city and identifying which residents are permanent and which are just passing through. Both kinds of information are useful, but they are answers to different questions. The most recent chapter in the story of the Milky Way's outer boundary involves a survey that was specifically designed to push the detection of halo stars to greater distances than any previous instrument had achieved. The Dark Energy Spectroscopic Instrument, known as DESI, began full survey operations in 2021 and has been systematically measuring the spectra of millions of objects across a large fraction of the sky. Among its targets are distant halo stars, including RR Lyrae variables and a class of evolved giant stars that are intrinsically luminous enough to be detected at enormous distances. Preliminary results from Deason and related programs have extended the census of Milky Way halo stars to distances approaching 500,000 light-years from the galactic center in some directions, and have found evidence for stellar overdensities at these extreme radii that may represent the outermost wraps of the Sagittarius stream, recently accreted material from other satellite galaxies, or previously unknown structures in the outer halo that have not yet been characterized. The data are still being analyzed, and the full picture will not emerge for several more years. But the consistent trend across every survey that has pushed to greater depth and greater distance is the same. Every time we look further, we find more. Now, consider what this means for our mental image of the galaxy. Most of us, when we picture the Milky Way, think of the image that appears on the covers of astronomy books. The graceful spiral seen from above, its bright arms curving outward from a glowing central bar. The whole structure contained within a diameter of 100,000 light-years. That image is real. The bright disk it depicts genuinely exists. The spiral arms are real. The bar is real. The disk is where most of the galaxy's stars live, where most of its star formation is happening right now, where the interstellar medium is densest and most chemically complex, where planetary systems like our own are most common. But that image captures perhaps 5 to 10% of the galaxy's true spatial extent and an even smaller fraction of its true mass. The luminous disk, spectacular as it is a small, dense core embedded within a vastly larger structure that is mostly dark, mostly empty by the standards of the disk, and mostly invisible to any instrument that detects only visible light. The true galaxy, the full gravitationally bound structure from center to virial radius, is something that no single image has ever captured, and that no human eye has ever seen, because most of it emits no light detectable by the human eye, and because we are inside it, unable to step outside and look at it whole. This invisibility of the true galaxy is not just a technical inconvenience, it reflects something deep about the nature of the universe. The ordinary matter that makes up stars, planets, and gas, the matter made of protons and neutrons and electrons, the matter that participates in electromagnetism and therefore emits and absorbs light, constitutes only about 15 to 16% of the total matter content of the universe. The remaining 84 to 85% is dark matter, which interacts gravitationally but not electromagnetically, and which is therefore completely invisible to any telescope that detects light in any wavelength. The dark matter halo of the Milky Way is not an unusual feature of our particular galaxy. It is a universal feature of all galaxies, a consequence of the fact that the universe is overwhelmingly made of something we cannot see and do not fully understand. What we call the Milky Way in our everyday conception of it is the luminous minority embedded within a dark majority. The stars and gas of the disk, for all their spectacular complexity and beauty, are a thin frosting on a vast, dark cake. The real mass, the real gravitational influence, the real spatial extent of the galaxy is contained in a structure we cannot image directly, can only infer from its gravitational effects on the things we can see, and are still in the process of mapping with ever more sophisticated tools. This is not a cause for frustration, it is a cause for wonder. The fact that humanity, using instruments built over the course of just a few centuries of scientific development on a small planet orbiting an ordinary star in the outer reaches of a galaxy, whose true scale we are only beginning to comprehend, has managed to infer the existence, the mass, the extent, and even the rough shape of this invisible structure, is one of the most extraordinary intellectual achievements in the history of our species. We cannot see the dark matter halo. We have never touched it, never directly detected a single dark matter particle. And yet, we know it is there. We know roughly how massive it is. We know roughly how far it extends. And we know this with a confidence that is justified by multiple independent lines of evidence converging on the same answer. The history of that convergence, the story of how we went from not knowing the dark matter halo existed to mapping its properties with reasonable precision, is itself a story worth telling in full, because it illustrates something important about how scientific understanding actually advances, not through single dramatic revelations, but through the slow accumulation of evidence from many directions, each piece constraining the possibilities a little more, until the picture that remains is the one that fits all of the available data. The accumulation of evidence for the dark matter halo's properties did not follow a straight line. It followed the irregular, sometimes frustrating, sometimes exhilarating path that characterizes all genuine scientific progress, where the same question is approached from multiple directions simultaneously, where different methods sometimes give conflicting answers, and where resolving those conflicts requires either better data, better models, or a willingness to reconsider assumptions that seemed too well established to question. In the case of the Milky Way's mass and extent, the conflicting answers were not subtle. For much of the first 2 decades of the 21st century, 2 broad classes of measurement consistently gave different results. Methods based on the kinematics of traces in the inner halo, meaning the velocities of objects within roughly 100,000 light-years of the galactic center, tended to produce lower mass estimates, clustering around 500 billion to 800 billion solar masses for the total mass of the Milky Way, including its dark matter halo. Methods based on the kinematics of objects in the outer halo at distances greater than 100,000 light-years tended to produce higher mass estimates, clustering around 1.2 trillion to 2 trillion solar masses. This discrepancy was not simply a matter of measurement error. It reflected a genuine tension between what the inner halo was telling us about the galaxy's mass distribution and what the outer halo was telling us. Resolving it required understanding whether the mass distribution within the halo is smooth and follows a simple mathematical profile, or whether it is more complex, with features that different measurement methods were sensitive to in different ways. The mathematical profiles used to describe dark matter halos are called density profiles, and they specify how the density of dark matter changes with distance from the center of the galaxy. The most widely used profile in the literature is named after Julio Navarro, Carlos Frenk, and Simon White, the three astronomers who derived it from computer simulations of structure formation in the late 1990s. The Navarro-Frenk-White profile, as it is universally known in the field, predicts that dark matter density falls off as roughly the inverse square of the distance from the center in the outer regions of a halo, following a specific mathematical form that emerged naturally from simulations of how halos form through hierarchical merging in a universe dominated by cold, dark matter. The profile fits many observations well, but fitting a profile to data is a process of finding the best compromise across all the data points, and different data points at different radii can pull the fit in different directions. When the mass estimates from the inner and outer halo disagreed, it suggested either that the profile was not as smooth and regular as the simulations predicted, or that some of the measurements were affected by systematic errors that had not been properly accounted for. One major source of systematic uncertainty in outer halo mass measurements is the question of whether the tracers being used are actually in dynamical equilibrium with the galaxy's gravitational potential. Dynamical equilibrium is the condition in which the statistical properties of a population of objects, their average velocities, the spread of their velocities, the distribution of their orbital shapes, are stable over time and reflect the underlying gravitational potential in a predictable way. Most of the mathematical machinery used to convert observed velocities into mass estimates assumes dynamical equilibrium, but the outer halo, as we have already seen, is not in equilibrium. It contains stellar streams, recently accreted material, and objects that are still settling into their final orbits after disturbances caused by past merger events. The Sagittarius stream alone contributes stars to the outer halo that are on highly eccentric, non-equilibrium orbits, moving faster near their closest approach to the galactic center and slower near their most distant point. If a mass estimation method samples a region of the halo that is disproportionately populated by such non-equilibrium objects, it will produce a biased answer. The Gaia satellite helped resolve some of these systematic issues by providing proper motion measurements for halo stars and satellite galaxies, meaning measurements of their motion across the plane of the sky rather than just their motion toward or away from us along the line of sight. Before Gaia, most velocity measurements of distant halo objects were one-dimensional, capturing only the radial velocity component. This is sufficient for some purposes, but leaves a significant degeneracy in the mass estimation, because the same observed radial velocity distribution can be produced by different combinations of total mass and orbital anisotropy, which is the degree to which orbits in the halo are preferentially radial or tangential. Proper motion measurements from Gaia broke this degeneracy for many objects in the inner and middle halo. For satellite galaxies and globular clusters within roughly 150,000 light-years of the galactic center, Gaia provided full three-dimensional velocity vectors, allowing mass estimations that were far less sensitive to assumptions about orbital anisotropy. The results from these improved measurements converged on a mass estimate for the Milky Way of approximately 1.1 to 1.3 trillion solar masses, with the most carefully constructed analyses clustering around 1.2 trillion solar masses as the best current estimate. This is roughly 60% larger than the Sun's mass multiplied by a trillion, and it is dominated almost entirely by dark matter. The stars of the Milky Way, all several hundred billion of them, contribute only about 50 to 60 billion solar masses to this total, roughly 4 to 5% of the galaxy's mass budget. The gas and dust of the interstellar medium contribute another 10 billion or so solar masses. Everything visible, everything that emits or reflects light, constitutes perhaps 5 to 6% of the Milky Way's total mass. The remaining 94 to 95% is dark matter, invisible, detectable only through its gravitational influence on the luminous minority. The corresponding virial radius for a halo of this mass, calculated using the standard definition where the mean density within the virial radius equals 200 times the critical density of the universe, comes out to approximately 650,000 to 800,000 light-years. The diameter of the gravitationally bound Milky Way system is therefore somewhere between 1.3 million and 1.6 million light-years, using this definition and this mass estimate. More generous definitions of the boundary and higher mass estimates push the number toward 2 million light-years. To translate that into terms that might make the scale more visceral, consider the following. If the Milky Way's luminous disk, 100,000 light-years across, were shrunk to the size of a dinner plate 30 centimeters in diameter, the virial radius of the dark matter halo at 800,000 light-years would extend to a distance of 2.4 meters from the center of the plate in every direction. The full halo would fill a sphere nearly 5 meters across. The dinner plate, the part of the galaxy that appears in every artist's illustration and every textbook photograph, would be sitting at the center of a structure 16 times wider than itself, most of which would be completely invisible. Now, hold that image and add the circumgalactic medium, the hot gas corona that extends even beyond the dark matter halo's densest regions. Its full extent is less precisely known, but estimates based on X-ray observations and absorption measurements of background quasars, which are distant luminous objects whose light passes through the circumgalactic medium on its way to our telescopes, suggest it extends to perhaps 1 million light-years or beyond in some directions. On our dinner plate scale, that would add another half meter in every direction, creating a haze of extremely hot, extremely diffuse gas extending 3 meters from the center of the plate. The circumgalactic medium is not merely a passive reservoir. It is an active participant in the galaxy's ongoing life cycle. Supernova explosions in the disk launch hot gas outward at hundreds of kilometers per second, injecting energy and chemically enriched material into the circumgalactic medium. The central supermassive black hole during episodes of enhanced accretion can drive outflows even more powerful, pushing gas to enormous distances. These outflows are thought to be one of the primary mechanisms by which galaxies regulate their own star formation rate, expelling gas that would otherwise cool and fall back into the disk, temporarily reducing the fuel supply for new stars. At the same time, gas from the circumgalactic medium and beyond is continuously raining back down onto the disk, the so-called galactic fountain cycle, operating over timescales of hundreds of millions to billions of years. Gas is ejected, rises into the halo, cools, and falls back, enriched by the heavy elements it picked up during its time in the outflow. This cycling of gas between the disk and the halo is one of the most important processes governing the long-term chemical evolution of the galaxy, and understanding it requires understanding the full extent and physical state of the circumgalactic medium, which in turn requires observations across a wide range of wavelengths from radio to X-ray. What emerges from all of this, from the kinematics of halo stars, the dynamics of satellite galaxies, the morphology of stellar streams, The mass estimates from Gaia and Hubble, the extent of the hot gas corona, the ongoing disruption of the Magellanic Clouds and the Sagittarius Dwarf is a portrait of the Milky Way as an entity of almost incomprehensible complexity and scale, not a simple disk of stars, not even a disk plus halo, but a layered, dynamic, evolving system of nested structures, each with its own physics, its own history, its own future, all gravitationally bound together into a single, coherent object that we call, with inadequate simplicity, our galaxy. There is a moment that occurs sometimes when you have spent long enough with a subject this vast, when the numbers have accumulated and the structures have been described and the history has been laid out in sufficient detail, when something shifts in how the information sits inside you. It stops being a collection of facts and becomes something closer to a feeling. Not an emotion in the ordinary sense, something more like a change in the perceived scale of your own existence, a sudden and vertiginous awareness of where you actually are and what you are actually inside of. You are on a planet orbiting a star. That star is one of somewhere between 200 and 400 billion stars in the luminous disk of the Milky Way. That disk, the part of the galaxy that contains essentially all of those stars, is approximately 100,000 light-years across and roughly 1,000 light-years thick in the region where the Sun sits, thinning toward the edges. It is an extraordinary structure by any measure available to human intuition, and it is, as we have now thoroughly established, a small fraction of the true extent of the system you are gravitationally bound to. Beyond the disk, extending outward in every direction to distances of hundreds of thousands of light-years, is the stellar halo, sparse and ancient, containing the dissolved remnants of dozens of galaxies that no longer exist as independent objects. Their stars now orbit within our galaxy's gravitational field, mixed almost beyond recognition into the background population of the halo, detectable only through the subtle statistical signatures of their shared orbital properties and the chemical fingerprints written in their spectra. You are living inside a structure that has consumed other galaxies. The Milky Way is not merely a galaxy, it is a graveyard of galaxies, a composite built from the bodies of structures that predated it, and it is still consuming more. The Sagittarius Dwarf is being torn apart right now, its stars joining the halo, even as you read these words, its core still intact, but diminishing with each orbital passage. Beyond the stellar halo, extending to distances of 600,000 to perhaps 1 million light-years from the galactic center, is the dark matter halo, the vast invisible structure that contains most of the galaxy's mass, that holds the luminous disk and the stellar halo and the satellite galaxies in their orbits, that defines the true gravitational boundary of the Milky Way. It is something that cannot be seen, cannot be touched, cannot be detected by any instrument sensitive to light in any wavelength. It is known only by inference, by the gravitational imprint it leaves on everything that moves within it. And yet it is more real, more massive, and more spatially dominant than everything else we have described combined. Beyond even the dark matter halo, pervading the space between the halo and the beginning of intergalactic space proper, is the circumgalactic medium, the hot, diffuse gas corona that breathes in and out with the galaxy's star formation activity, that contains a mass of material comparable to all the visible stars, that extends the galaxy's physical influence to distances approaching 1 million light-years in some directions. It is detectable only through its absorption of background light, its faint X-ray glow, the subtle distortions it imprints on the spectra of distant quasars whose light passes through it on the way to our telescopes. All of this, the disk and the stellar halo, and the dark matter halo and the circumgalactic medium, is one object, one gravitationally bound system, one galaxy, and it is between 1.3 million and 2 million light-years across, depending on where you draw the boundary and what physical definition you use to draw it. A light-year is the distance light travels in 1 year, moving at approximately 299,792 kilometers per second. In 1 year, light covers approximately 9.5 trillion kilometers. In 100,000 light-years, it covers 950 quadrillion kilometers. In 2 million light-years, it covers 19,000 quadrillion kilometers. These numbers are beyond the reach of human intuition to hold directly. They do not correspond to anything in everyday experience. There is no analogy that truly captures them. The best we can do is gesture toward their scale and acknowledge that the gesture is inadequate. What we can do, and what I think matters more than any specific number, is sit with the implication. The galaxy you live in is between 12 and 20 times larger than the version of it that most educated people carry in their minds. The object described in textbooks, the 100,000 light-year spiral, is real, but it is the luminous core of something vastly larger. The way a city's downtown is real but does not represent the full metropolitan area. The way a brain is real but does not represent the full organism it governs. The Milky Way has been systematically underestimated for most of the history of modern astronomy, not through carelessness or incompetence, but because the tools required to see its true extent did not exist until recently, and because the most extended structures are deliberately difficult to detect, diffuse and dark and sparse and cold or unimaginably hot in ways that require specific instruments and specific techniques to see it all. Consider what it took to arrive at the current picture. It required the development of radio astronomy, which allowed astronomers to see through the dust that blocks visible light and map the rotation of the galactic disk using the emission of neutral hydrogen at a wavelength of 21 centimeters. It required the development of charged particle detectors sensitive enough to measure the proper motions of stars with precisions measured in microseconds of arc, the angular equivalent of measuring the thickness of a human hair from a distance of several thousand kilometers. It required space-based X-ray observatories capable of detecting the faint thermal emission of gas at temperatures of millions of degrees Kelvin spread across volumes of hundreds of thousands of cubic light-years. It required survey telescopes capable of imaging hundreds of millions of stars and measuring their brightnesses in multiple wavelengths with photometric precision better than 1%. It required, above all, the mathematical and computational tools to extract meaningful physical information from these oceans of data, to separate signal from noise across the statistical complexity of 1 billion individual measurements, to model the gravitational dynamics of systems containing trillions of solar masses of matter distributed across millions of light-years of space. This is not a trivial achievement. It represents the accumulated effort of thousands of scientists across more than a century of work, each generation building on the tools and knowledge inherited from the previous one, each new instrument enabling measurements that were impossible with the previous generation's technology. Each new measurement forcing a revision or refinement of the picture inherited from the previous generation. The picture that has emerged from this cumulative effort is one that none of the astronomers who began it could have anticipated in full. They knew they were measuring something vast, They did not know how vast. They knew the dark matter halo existed. They did not know how far it extended. They knew the outer halo contained ancient stars. They did not know those stars were the dissolved remnants of dozens of distinct galaxies, each with its own history, each identifiable through the chemical and kinematic signatures preserved in the orbits of its former stars. The discoveries have consistently exceeded the expectations, and there is no particular reason to think we have reached the end of that pattern. The Vera Rubin Observatory, named for the astronomer whose rotation curve measurements did so much to establish the reality of dark matter, is currently in the process of beginning its legacy survey of space and time. A 10-year program to image the entire accessible southern sky repeatedly, building up a dataset of extraordinary depth and temporal coverage. It will find stellar streams that current surveys cannot detect, map the outer halo to distances and faint surface brightnesses that are currently inaccessible, and discover new structures whose existence we currently have no evidence for. The Roman Space Telescope, currently scheduled for launch in the mid-2020s, will extend the census of halo stars with a sensitivity and a field of view that dwarfs current capabilities. What these instruments will find, specifically, cannot be predicted. That is the nature of instruments that push into genuinely unexplored territory. But the consistent trend of the past 2 decades suggests that the answers will make the galaxy larger, more complex, and more ancient than our current best picture. Every time a new generation of instruments has looked further into the outer halo, it has found material that was not in the previous picture. Every time a new analytical technique has been applied to existing data, it has found structures that the previous analysis missed. The galaxy has a way of exceeding our expectations, and there is something deeply appropriate about that. We began tonight with a number. 100,000 light-years, the canonical diameter of the Milky Way, the number that has appeared in textbooks and encyclopedias and science documentaries for generations. It is not a wrong number in the sense that it describes something that does not exist. The luminous disk really is approximately 100,000 light-years across. The error is in treating that number as the answer to the question of how big the galaxy is, when in fact it is the answer to a much smaller question: how big is the part of the galaxy we can see most easily? The true galaxy, the full gravitationally bound system from its ancient core to its outermost boundary, is something between 1.3 million and 2 million light-years across. It contains, in its dark matter halo alone, somewhere around 1.2 trillion solar masses, of which only about 5% is luminous matter. It has consumed dozens of smaller galaxies over the course of its history, and it is in the process of consuming more right now. It is falling toward the Andromeda Galaxy in a collision that will eventually merge both structures into a single elliptical remnant. It is embedded in a local group of more than 50 galaxies, which is itself embedded in the Virgo supercluster, which is itself a small part of a structure called Laniakea, a supercluster of galaxies spanning approximately 500 million light-years that contains the mass of 100 million billion suns. And somewhere within all of this, at a distance of 26,000 light-years from the galactic center, on a roughly circular orbit that takes 225 million years to complete, orbiting a middle-aged yellow star of completely unremarkable properties, is a small rocky planet where, at some point in the last few 100,000 years, a species of primate developed the capacity for abstract thought, built instruments of extraordinary precision, and figured out, through patience and ingenuity and the willingness to follow evidence wherever it led, that the place they lived was almost incomprehensibly larger than it first appeared. That is not a small thing. In a universe of 2 million light-year galaxies and dark matter halos and ancient stellar streams, the fact that anything anywhere developed the capacity to measure those distances, to infer the existence of invisible structures from their gravitational effects on visible ones, to reconstruct the merger history of a galaxy from the orbital properties of individual stars, is perhaps the most extraordinary fact of all. Not because it changes the scale of the cosmos. It does not. The galaxy is exactly as large as it is, regardless of whether anything within it knows that. But because it means the universe contains, in at least one place, something capable of comprehending its own context. We are made of the same material as the stellar halo we have spent this time mapping. The heavy elements in our bodies were forged in the cores of stars that lived and died before the sun existed, scattered through the interstellar medium by supernova explosions, incorporated into the molecular cloud that collapsed to form the solar system 4.5 billion years ago. The iron in your blood was made in stellar explosions. The calcium in your bones was synthesized in the final stages of massive stars. The oxygen you are breathing was produced in the nuclear furnaces of stars that no longer exist. You are, in the most literal, physical sense, made of the Milky Way. And now, through the accumulated effort of centuries of human curiosity, you know something about the place you came from that no previous generation of humans knew. You know that it is larger than anyone thought. You know that it is older and more complex and more dynamic and more deeply connected to the history of the universe than the simple picture of a spiral disk of stars suggests. You know that the pale smear of light visible on a clear dark night, that ghostly band that has provoked wonder in every human culture that has ever looked up at it, is the luminous edge-on view of a disk that is itself just the bright core of something far vaster, most of which is dark and silent and extends to distances that no human eye will ever directly see. That knowledge does not diminish the wonder, it multiplies it. The galaxy you live in is not 100,000 light-years across. It is, in the fullest and most physically meaningful sense of the question, somewhere between 1.3 million and 2 million light-years across, and we are still learning where it ends.